Right now, in a lab in New Mexico, physicists just did something your entire intuition about the universe says is impoime and made it flow backward. Not in theory, possible. They took a system moving forward through T on paper, but inside a working quantum computer, and here's the part that should keep you up at night. Classical physics has no explanation for how this is even allowed. Before we get into what they actually did, you need to understand just how sacred the forward flow of time is supposed to be. Every single thing you have ever experienced tells you time moves in one direction. You wake up, you get older. A cup falls off a table and shatters into pieces, and no matter how long you wait, those pieces never leap back up and reassemble themselves into a cup. Smoke rises from a candle and disperses into the air, but it never gathers itself back together and dives into the flame. You remember what happened yesterday in vivid detail, yet you have absolutely no memory of tomorrow. This one-directional flow is so deeply woven into how we experience reality that most people never even think to question it. It just is. It is the water we swim in. But physicists have a name for this phenomenon, and they have spent more than a century trying to understand where it actually comes from. They call it the arrow of time. And the strange thing is, when you look at the fundamental equations that govern the universe at the smallest scales, that arrow doesn't actually appear anywhere. The core laws of physics, the equations describing how particles move and interact, work exactly the same whether you run them forward or backward. Watch a video of two billiard balls colliding, then play that video in reverse. Both directions look completely physically plausible. There's nothing in the mathematics that says one way is right and the other is wrong. Nothing prevents a planet from orbiting its star in reverse in a purely idealized model. Time, at the most basic mathematical level, appears to be symmetric. So, if the equations don't care about direction, why does our entire lived experience feel so relentlessly one way? The answer physicists arrived at involves a concept called entropy, which is essentially a measure of disorder in a system. The second law of thermodynamics tells us that in any closed system, entropy tends to increase over time. Things move from order to disorder, not the other way around. A tidy room left alone will drift toward mess, never the reverse, unless someone actively puts in the energy to organize it again. This tendency toward increasing disorder is what physicists believe actually creates the arrow of time we experience. It's not that the fundamental laws forbid reversal, it's that reversal is so staggeringly improbable, given the astronomical number of ways a system can become disordered, compared to the vanishingly small number of ways it can spontaneously become ordered again, that in practice we simply never see it happen. Given enough time and enough particles, in theory, a shattered cup really could reassemble itself. It would just take longer than the age of the universe, many times over, for the odds to ever fall in its favor. This is where quantum mechanics enters the story and changes everything, because the rules that govern very small systems, systems made of individual particles like electrons and photons, are strange enough that some of our everyday assumptions about entropy and disorder start to bend in ways that classical physics simply cannot account for. Think about what that actually means for a moment. At the scale of atoms and photons, particles don't behave like tiny billiard balls with a fixed position and a fixed speed. They exist as a kind of smeared-out probability, occupying many possible states at once, until something forces them to settle into one outcome. This is the famous strangeness of quantum superposition, and it's part of why quantum computers are so powerful in the first place. A regular computer bit is either a 0 or a 1. A quantum bit, a qubit, can exist as a blend of both simultaneously, at least until it's measured. And it's precisely this fragile, probabilistic nature that gives physicists a foothold to try something as audacious as nudging a system's evolution backward. In a classical system made of trillions of particles bumping into each other randomly, there's no realistic way to track, let alone reverse, every single interaction. But in a quantum system built from just a handful of carefully isolated particles, with almost every variable under direct experimental control, the odds shift dramatically. Suddenly, reversing the flow becomes not just theoretically possible, but something you might actually be able to engineer in a lab, with the right hardware and the right algorithm. For decades, physicists have used a famous thought experiment to probe these boundaries. It's called Maxwell's demon, named after the 19th century physicist James Clerk Maxwell, who imagined a tiny, intelligent being capable of sorting fast-moving and slow-moving gas molecules into separate chambers without expending any energy, which would appear to violate the second law of thermodynamics by decreasing entropy for free. For over a century, this remained a paradox designed to test the limits of the theory. Physicists eventually resolved the apparent contradiction by realizing that the demon itself has to gather and store information about each molecule in order to sort it, and that information has to be erased eventually, which costs energy and generates entropy somewhere else in the system. In other words, the universe still balances its books, just not in the place you'd initially expect. But even after that resolution, The thought experiment kept nagging at physicists because it hinted that information itself, not just energy and matter, might be a fundamental physical resource, something that could be converted, stored, and spent, almost like a currency built into the fabric of reality. That idea sat mostly in the realm of theory for most of the 20th century, but recent breakthroughs in quantum information science have started turning Maxwell's demon from a philosophical puzzle into something researchers can actually build and test using real quantum hardware, transforming a century-old riddle into a working laboratory tool. That brings us to the two experiments driving the current wave of headlines, and it's worth understanding both because together they tell a much richer story than either one alone. The first happened back in 2019 when an international team of physicists, including researchers connected to Argonne National Laboratory and institutions in Russia and Switzerland, published a paper in the journal Scientific Reports with a bold and immediately controversial title, Arrow of Time and its Reversal on the IBM Quantum Computer. What they did was construct a tiny quantum system using just 2 qubits, the basic building blocks of quantum information, standing in for the behavior of a localized electron. In quantum mechanics, particles are described not by a fixed position, but by something called a wave function, a mathematical object, representing every possible state the particle could occupy, and the probability of finding it there. Normally, as time passes, that wave function spreads outward, becoming more diffuse and less localized, much like ripples spreading across a pond after you drop in a stone. The researchers then designed an algorithm running on an actual IBM quantum computer that attempted to reverse this spreading process for every single component of the wave function simultaneously, essentially trying to pull that expanding ripple back into the single point where it started. Remarkably, it worked, at least some of the time. In their 2-qubit setup, the system successfully returned to its original localized state 85% of the time. That number alone is startling because it suggests that under the right controlled conditions, a quantum system really can be nudged backward toward an earlier, more ordered state, something the second law of thermodynamics would seem to forbid in any classical everyday context. But when the researchers pushed further and added a 3rd qubit to make the system slightly more complex, the success rate collapsed to 50%. The added complexity introduced more opportunities for entropy to creep back in, and the quantum computer's imperfect control over every component of the larger system made a clean reversal much harder to pull off. The bigger and more complicated the system became, the less reliably time could be coaxed backward. This pattern itself became one of the most important findings of the study because it hinted at something deeply important. Reversing time isn't forbidden by the laws of physics, but it becomes exponentially harder as the system grows, which is exactly why we never see it happen naturally in the massive, complicated, particle-rich world we actually live in. The researchers went even further, running a thought experiment to put this improbability into perspective. They calculated that if you were to observe 10 billion freshly localized electrons every single second for the entire 13.7 billion year lifetime of the universe, you would expect to see a spontaneous reversal of this kind happen only once. And even then, it would only push the system backward by about 1/10 billionth of a second, roughly the amount of time between a traffic light turning green and the driver behind you honking their horn. In other words, spontaneous time reversal in nature is not just rare. It is so absurdly, cosmically unlikely that for all practical purposes, it might as well be impossible without direct, deliberate intervention using something as precise and controllable as a quantum computer. Naturally, headlines exploded. Scientists reverse time. Physicists build a time machine. But not everyone in the physics community was convinced the framing was accurate. And this is where the story gets more interesting, because good science reporting means looking at the pushback too. Critics, including a widely read rebuttal published by MIT Technology Review, argued that calling this a genuine reversal of time was a significant overstatement of what actually happened. Their point was subtle but important, because the underlying quantum equations are already time-symmetric, meaning they work equally well forward and backward. Engineering a system to trace its steps back to an earlier state isn't quite the same as making time itself run backward in any deep physical sense. It's closer to carefully reconstructing a specific earlier configuration using total, precise control over a small, isolated system, rather than time genuinely reversing its flow for the universe at large. Critics compared it to reversing a video of a billiard ball collision. It looks plausible, and mathematically, it obeys the same rules either direction, but nobody would say the universe is running backward just because the footage does. This is an important nuance, and any honest telling of this story has to include it, because it separates real scientific insight from misleading marketing. Still, even the skeptics acknowledged the value of the underlying work. One physicist not involved in the study, James Whitfield of Dartmouth College, called it a nice contribution to the foundations of physics, and that's really the heart of it. The 2019 experiment wasn't really about building a time machine at all. It was about demonstrating, in a real physical quantum system, that entropy can in fact be locally and temporarily reversed if you have precise enough control, and that the difficulty of doing so scales dramatically with the size and complexity of the system. That's a genuinely important insight into how our universe transitions from the time-symmetric rules of quantum mechanics to the one-directional arrow of time we experience in everyday life. Now fast forward to more recent research, where scientists, including a team connected to Los Alamos National Laboratory, published new findings in the prestigious journal Physical Review X, taking this idea even further and turning it from an abstract curiosity into something with genuine practical potential. Instead of simply demonstrating that reversal was possible, this newer research developed precise quantum control techniques that allow scientists to actively reshape a system's arrow of time by carefully managing the process of quantum measurement itself. In quantum mechanics, the very act of measuring a system can change its state, a strange and famous feature of the theory that has no real classical analog. What this newer work showed is that by controlling exactly how and when measurements are taken, researchers can steer a quantum system's evolution in ways that mimic time running in reverse, and in doing so, extract usable energy from the measurement process along the way. To really appreciate why this matters, it helps to understand what a quantum measurement actually costs, in physical terms. Every time you measure a quantum system, you're forcing it to collapse from a fuzzy blend of possibilities into one concrete outcome, and that act of forcing a decision has real thermodynamic consequences. It takes energy to measure, and it releases energy or information depending on how the measurement is designed and timed. For most of the history of quantum experiments, measurement was treated as an unavoidable disturbance, something scientists had to work around, a necessary evil that destroyed the delicate quantum information they were trying to preserve. What this newer research flips on its head is the assumption that measurement is purely disruptive. Instead, by choosing exactly when to measure, how strongly to measure, and in what sequence, researchers found they could turn what used to be considered a destructive nuisance into a controllable resource, one that can be used to steer a system's statistical behavior and, in the process, pull useful energy out of what would otherwise be lost. This is a genuinely exciting development because it connects directly to something called a quantum battery, a theoretical device that stores and transfers energy using quantum effects, potentially far more efficiently than any conventional battery ever could. If researchers can reliably harvest energy from carefully controlled quantum measurements, essentially turning the strange behavior of quantum systems into a usable energy resource, it could open the door to entirely new categories of technology, from more efficient quantum computers that manage heat and energy loss more effectively, to genuinely novel forms of energy storage inspired by principles that simply don't exist anywhere in classical physics. One of the researchers involved, describing the theoretical backbone of the work, explained that the governing equations function just as well if you reverse time, which is precisely why quantum systems offer these strange new opportunities that are simply unavailable anywhere in the classical world we're used to. So what does all of this actually mean, put together? It means physicists have found a real, demonstrated, repeatable way to manipulate quantum systems so that they behave in a very specific and carefully controlled sense, as though time is running backward. It means this isn't a violation of the laws of physics, but rather a clever exploitation of a loophole that has existed in the mathematics all along, one that only becomes accessible when you have exquisite control over an extremely small, isolated system. It means the boundary between the time-symmetric world of quantum mechanics and the one-directional world of everyday experience is far blurrier and more negotiable than most people ever realized. And it means classical physics, the physics of falling apples, orbiting planets, and shattering teacups, genuinely has no framework for explaining how or why this is possible. Classical thermodynamics assumes entropy only increases. It has no mechanism, no vocabulary, no equation that accounts for a system reaching backward toward a more ordered past state on command. That gap, that genuine explanatory silence from classical physics, is exactly why this research keeps making headlines and exactly why it keeps causing arguments among physicists about what language is appropriate to describe it. Some researchers prefer cautious, technical phrasing, describing the work as reshaping a system's statistical arrow of time under controlled conditions. Others, especially those talking to journalists and general audiences, reach for punchier language, because saying scientists reverse time captures public attention in a way that dense thermodynamic terminology never will. Both descriptions are, in a sense, correct. They're just aimed at different audiences, and that tension between precise scientific language and attention-grabbing headlines is exactly why stories like this one tend to spiral into confusion the moment they leave the pages of a physics journal and land in front of a general audience. It's worth being clear about what this is not, because that matters just as much as what it is. This is not time travel in the science fiction sense. Nobody is stepping into a machine and walking out in the past. Nobody has built anything that lets information, people, or matter travel backward through time in any way that would let you change history or meet a younger version of yourself. What's actually happening is something more subtle and, in many ways, more scientifically profound. A tiny, isolated quantum system being coaxed, through extraordinarily precise control, into revisiting an earlier state of itself, in defiance of what our everyday intuition about disorder and decay would predict. It is real. It has been demonstrated on actual hardware, not just simulated on paper, and it does reveal something true and strange about the deep structure of physical law, but it operates within the bounds of quantum theory, which already permitted this kind of behavior mathematically. It doesn't rewrite the rules. It finds a way to use them that nobody had managed to engineer before. It's also worth remembering just how young this entire field still is. Quantum computers themselves, the actual physical machines capable of running experiments like these, have only existed in any usable form for a little over a decade, and the versions available today are still small, noisy, and prone to errors compared to the room-sized 1,000-qubit machines researchers dream about for the future. Every experiment like the ones we've just walked through, whether it's the original 2-qubit demonstration in 2019 or the more recent measurement-based energy harvesting work, is essentially a proof of concept, a small-scale demonstration meant to show that an idea works in principle long before it becomes something practical enough to sit inside a commercial device. That's an important thing to hold on to whenever headlines get dramatic. The gap between a laboratory curiosity involving 2 or 3 qubits and a genuinely useful piece of technology involving thousands of them is enormous. And closing that gap will likely take years, possibly decades, of steady, unglamorous engineering work. But every major technology humans have ever built started exactly this way, as a strange, barely functional demonstration in a lab, long before it became something ordinary people relied on without a second thought. There's also a broader philosophical layer to all of this that's worth sitting with for a moment. For most of human history, the arrow of time was treated as one of the most fundamental, unquestionable features of reality, right up there with the constancy of the speed of light or the conservation of energy. The idea that scientists could, even in a narrow and carefully controlled way, push back against that arrow inside a laboratory forces us to reconsider just how much of what feels absolute and unbreakable about our universe is actually a statistical tendency rather than an ironclad law. Entropy increasing isn't a command from the universe. It's simply the overwhelmingly most probable outcome given how many ways there are for things to become disordered compared to how many ways there are for them to become ordered. When you shrink a system down small enough and control it precisely enough, that overwhelming probability can, for a brief moment, be pushed in the other direction. It also reframes something most of us have simply accepted without question since childhood, the idea that the past is fixed and unreachable, while the future remains open and undetermined. That distinction feels obvious, almost too obvious to even state out loud. But strip away the intuition and look purely at the mathematics, and that asymmetry starts to look less like a hard law of nature and more like an emergent property of scale, an accident of just how many particles happen to make up the ordinary objects we interact with every day. Shrink the system down far enough, control it precisely enough, and that supposedly unbreakable asymmetry starts to soften. That doesn't mean the past and future become interchangeable in any practical sense for creatures like us, made of trillions upon trillions of atoms interacting in wildly complicated ways. It means the boundary between what's fixed and what's flexible depends heavily on how much control you have over the system you're looking at, and quantum computers happen to be one of the very few tools humanity has ever built that offer that kind of fine-grained control over individual particles. That single idea has implications reaching far beyond a physics laboratory. If researchers can continue to refine these techniques, if they can extend the same level of control from 2 or 3 qubits to systems with hundreds or even thousands of qubits, which is the direction the original 2019 research team explicitly said they wanted to take this work, we could be looking at meaningful improvements in how quantum computers manage errors, dissipate heat, and maintain the fragile quantum states they depend on to function. Quantum computers are notoriously sensitive to their environment. The tiniest disturbance can cause what's known as decoherence, where a delicate quantum state collapses into a much more ordinary classical one, destroying the information it was carrying. Any technique that gives researchers finer control over how a quantum system evolves through time, even one as exotic sounding as reversing its arrow of time, is potentially a tool for fighting back against that fragility, for holding a quantum computation together just a little bit longer, or for extracting a bit of useful energy from a process that would otherwise simply be lost as unusable heat. And that's really the story underneath the sensational headline. This isn't really about defeating time. It's about scientists discovering piece by piece that the rules governing the smallest building blocks of our universe are far stranger, far more flexible, and far more useful than classical physics ever suggested they could be. Every one of us grows up assuming the arrow of time is an unbreakable law, as fixed and immovable as gravity itself. And now, in laboratories in New Mexico and beyond, using nothing but carefully engineered qubits and painstakingly controlled measurements, physicists are showing that under the right conditions, at the right scale, with the right level of control, that arrow can bend, not break, not reverse for the universe as a whole. But bend in a small, isolated, laboratory-controlled pocket of reality, just enough to prove that our everyday intuitions about time were never the whole story. So the next time you drop a cup and watch it shatter, and some small part of you wonders whether those pieces could ever leap back together, remember this. Classical physics will tell you, flatly and without hesitation, that it's essentially impossible, and for all practical purposes in our macroscopic world, that's still true. But somewhere in a quantum lab, on a system small enough and controlled precisely enough, scientists have already shown that the impossible isn't always as impossible as we thought. They haven't broken the laws of physics. They've found the one narrow door those laws left open, a door that classical physics never even knew existed, and they've started walking through it. What they find on the other side, in terms of quantum batteries, error-resistant quantum computers, and technologies we haven't even imagined yet, may end up mattering far more than the reversal of time itself. Because if this is what happens when scientists learn to bend the arrow of time just slightly, it raises an obvious and unavoidable question. What else, buried deep in the strange mathematics of the quantum world, is waiting for someone precise enough, patient enough, and bold enough to discover? We are still, in many ways, at the very beginning of understanding what quantum systems are truly capable of. Every decade seems to bring another discovery that quietly reshapes what we thought was fixed and unchangeable about reality. And this one, small as it may seem when confined to a couple of qubits in a lab, is no different. Keep watching this space, because the physicists behind this work have already said they're aiming for bigger systems, bigger machines, and bolder experiments next. And if the past decade of quantum research has taught us anything at all, it's that today's laboratory curiosity has a habit of becoming tomorrow's foundational technology, quietly, steadily, one carefully controlled qubit at a time, until the impossible simply becomes the new normal.